Hi everyone. Today I will show you how we use matrix diagonalization to solve differential equations, particularly those arising in control systems, in the form of state space equations. In the future years, we will meet many state space equations in control systems learning. So be careful to watch my next demonstration. Here, I will give you a system of two differential equations for example. This is a system of two coupled first-order differential equations, which is common in state space models in control engineering. Y is the derivative of x1 with respect to t equals x1 plus x2. The derivative of x2 with respect to t equals 4 times x1 minus 2 times x2. We can rewrite it as the time derivative of the state vector x1, x2 equals the system 2 by 2 matrix 1, 1, 4, negative 2 times the state vector x1, x2. Or more compactly, we can write it as x dot equals A times x, where A equals the 2 by 2 matrix and x equals the state vector x1, x2. To solve this, we use a clever substitution. Let x equals p times y, where p is the matrix of eigenvectors of A, and y is a new coordinate system. This transformation will decouple the system and make it much easier to solve. Differentiating both sides, we can get x dot equals p times y dot, and A times x equals A times p times y. In the previous video, we have found that the diagonal matrix lambda of matrix A is 2 by 2 matrix, which is 2, 0, 0, negative 3. Substituting into the original equation, x dot equals A times x. Then we get p times y dot equals A times p times y. Next, multiply both sides by inverse of matrix P, because inverse of P times P equals identity matrix, and the inverse of P times A times P equals diagonal matrix lambda. So, we simplify the system to y dot equals lambda times y. We have solved the matrix lambda, so y dot equals 2, 0, 0, negative 3 times y. Now, the equations become very simple. y1 dot equals 2 times y1, and y2 dot equals negative 3 times y2. Their solutions are y1 equals c1 times the exponential of 2 times t, and y2 equals c2 times the exponential of negative 3 times t, where c1 and c2 are arbitrary constants determined by initial conditions. Finally, recalling that x equals p times y, and p is the coordinate transformation matrix of matrix A. We get it in the last video. Then, calculate the matrix P times vector y, and we will get the solution for the state vector x, as shown in the figure. This demo is very clear to show how we use eigenvalue and eigenvector to solve state space equations. This is very basic knowledge and widely used in control systems. That's all for today's video. Thank you for watching. See you next video.